and I want to introduce you to him. Jared Parker has HVAC training and a commissioning background in retro commissioning. He worked for Michigan State University in the capacity of a consultant as a project manager for retro commissioning from 2011 to 2013. Then in 2013, the ongoing commissioning program at MSU was implemented, and he was hired as an ongoing commissioning lead to drive the ongoing commissioning efforts on campus, including automated fault detection and diagnostics, predictive analysis, performance monitoring, dashboarding, control sequence optimization, and equipment performance optimization. He's been involved with various efforts, including Lawrence Berkeley Lab and Department of Energy initiatives, as well as the Big Ten and Friends Control Group. So with that, I would love to have you, Jared, speak about your experiences.
Hi, I'm Jared. You can go ahead and skip to the next slide.
Okay, great.
So as mentioned in my little bio there, I started here in 2013 with the fault detection and diagnostics program. Prior to that, we had a commissioning services department that was put together in 2007, but that was primarily focused on either doing energy audits for existing buildings or making sure that the construction of new buildings was going well. One of the things about ongoing commissioning is it kind of fills the gap between either a retro commissioning project and another retro commissioning project, or a new construction project and a retro commissioning project. Fault detection specifically is valuable for that ongoing commissioning process because it's constantly watching the operation of the building, and it's actually what's telling us, you know, the performance either of a particular piece of equipment or of the building as a whole is starting to slip, and it gives us an idea of the building health and when we should go back and either perform, you know, like a mild retro commissioning on a particular system or on the building as a whole. Next slide. So I wanted to give you a little information about MSU because it pretty heavily influenced what our scope was when we decided to implement fault detection. We've got our own power plant, so we produce a majority of our utilities on campus. We use steam for electrical generation. We then use that waste steam in the winter to heat a majority of buildings on campus. And then in the summer, there's quite a bit of steam-driven chilled water that is produced from that same steam. We do have a centralized control room where the majority of buildings are connected and they all report back. And we have 7 operators that monitor our equipment day in and day out for alarms and other operational issues that are more emergency issues. Because of the age of our campus, we have some buildings that are, you know, just a couple years old. In fact, we have like 2 buildings that are in construction right now. But we also have a number of buildings that range beyond 100 years in age. So we have quite an array of control systems on campus. This means that a lot of times our data collection can be really limited. And, you know, our lowest standard that I'm aware of is 9600 baud, which is about 0.0009 megabytes a second, to give you a little bit of an idea of how slow that is. We do have over 1,200 DDC connected pieces of equipment. Next slide. So because of these factors where we're generating a lot of our own utilities, we have, you know, a very engaged central control operational staff and sometimes very limited communications. We aimed our scope pretty specifically at just the large pieces of equipment, so air handlers and chillers and heat exchangers, but not really at the sort of things that tend to condition rooms. because we weren't sure that we could bring that kind of bandwidth in and what kind of effect it would have on our system health. We also wanted to focus primarily on HVAC equipment because HVAC equipment can be anywhere from 20 to 60% of the energy used in the building. And because we've already got these control systems in place, we have a lot of data that's already available for these systems. Because we had this large control room with people that are watching the alarms and the more emergency scenarios, we decided rather than trying to duplicate that, we wanted to look for faults that were related to inefficient operation, operational issues, or things that could be safety concerns. And these range from lab pressurization to inappropriate set points, or control systems that just aren't controlling the way that we intended them to due to changes over time. Once we started looking at what we could do with our fault detection system, we realized that we really needed a utility meter validation system, and we're using our fault detection platform for that. Because we are our own utility, the vast majority of our meters on campus are our meters, so we're watching that data, and we wanted to automate that process so that we can catch inconsistencies in the reported data more quickly. And then finally, because we have a lot of stakeholders that are involved, we wanted to be able to build our own visualizations. Our operators in the control room have different needs than the tradespeople, and then our leadership wants to see different things than what is useful for the operator and the tradespeople. Next slide. So MSU has actually been evaluating advanced analytics in one form or another since the early 2000s. First, we actually took data from our control system and sent it in the form of Excel files off to engineers from a firm to look at the data and help us identify operational issues. And then over time, we started looking at automated systems. Due to our in-house engineering and controls expertise, we decided that we wanted to self-perform. We also have had some less than stellar interactions with some third-party service providers, so that kind of reinforced the idea that we wanted to self-perform. We wanted to be able to maintain and implement as much as possible in-house. We also really wanted to own the software as opposed to a software as a service. Even though there's a higher initial capital investment, it usually means a lower yearly investment because you're just really paying for the licensing as opposed to a full-fledged service. We knew that we were going to have dedicated staff to run the ongoing commissioning program in general. So we thought that we'd really like to leverage that staff internally to better understand and respond to our systems, since somebody that's on site can interact with the operators and the tradespeople quickly and directly in order to make changes, as opposed to having to submit a change to a third party that is then going to try and make adjustments. There's a communication delay that's kind of inherent to that we wanted to avoid. And then lastly, we wanted to self-perform so that we couldn't be held captive by an integrator or a vendor the way that we might have if we had a software as a service solution. Next slide. So ultimately, we ended up going with a software provider called Iconics. And they're actually a SCADA company that is relatively recently ventured into the realm of HVAC fault detection. They're primarily a rules-based fault logic, but they are branching out into predictive analytics, which is also an area of interest for the university. It was advantageous for us to select a rules-based fault provider because we would be able to write our own faults with minimal training. The downside of rules-based faults is that they're a lot more limited in functionality than model-based faults because they don't make any future predictions They simply collect the data, and then you really do most of the interpretation. We did want to focus on faults that were more complex in operation than alarms, and rules-based faults are also not super great for detecting complex issues because they really can't fill in the gaps that a person looking at the system would. But at the time that we were looking in 2013, rules-based fault detection was a lot more mature than model-based fault detection, and so it felt like the most logical step for us to take its time. Next slide. So a little bit on what a rules-based fault is. It's really just a set of conditions that have to be met before a fault triggers. You can think of it as an alarm. In this particular instance, with an air handler, it's not as efficient to operate an air handler when you're both heating and cooling at the same time. So an example of a rules-based fault would look at, is my heating valve open and is my cooling valve open at the same time? And if so, trigger a fault, because that's an inefficient operation. I actually got an example here of actual fault logic that we've built. So if you look, you see it starts there with an if, and then there is a TOD, which means it's the unit on, that's time of day. If the outside air is above 60 degrees, and we have our heating valve open, and we have our cooling valve open for at least 15 minutes, then trigger a fault, because that is not an operation that we want to normally have happen. Slide. A couple of other fault examples that we have. One of them is an airflow station calibration fault. So in an air handler, we'll measure the amount of air that's coming back from the space, the amount of air that we're bringing in from outside to help ventilate, and then the amount of air that we're sending back out to the space. So at any given time, you should be able to compare the amount of air that's coming back from the space and the amount of air that's coming in from outside, and they should pretty much match with how much air is being supplied into the space. I felt like this has a lot of benefits. They include lower conditioning costs and fan operation costs. You can save conditioning energy if you are much warmer or much cooler outside than the temperature that you want in the space, because as you bring that air in, you'll be having to heat it or cool it further than you would if you were mixing the air better. And then fan operation costs can be saved because most systems will have a supply air set point and an outside air set point that they need to meet as a minimum. And if they're bringing in a lot more air than they think they are because the sensor's out of calibration, then we may be moving a lot more air. It uses a lot more fan energy to move that air, whereas if it was in calibration, we would not need nearly as much fan energy. There are some downsides to these types of faults, especially as a rule-based fault, because we rely on these sensors' accuracy in order to determine whether or not there's a fault condition. We make an assumption on where the sensor is located, and we also make assumptions on all of the sensors being accurate when we start. So implementation of something like this should really involve verifying those flow sensor locations and changing the fault logic if necessary to accommodate where the sensors are actually located. And then also, really, you need to go through and calibrate the sensors to make sure that you're starting from a known good position when you start to implement this type of fault. Slide. Another relatively simple fault that we've put into place is a temperature sensor. And we're really looking for one of two conditions here. Either the sensor itself has changed less than half a degree over 4 hours, which likely indicates that it may have failed or it is not reporting correctly. Or if we have multiple air sensors that are in the same air path, the temperature should match within a degree or so as you go through. So if one of those sensors or more of those sensors don't match, then that could indicate that there's a calibration issue with one or more of those sensors. Now again, like the airflow sensor, we have a lot of benefits of this because we're going to control the air handler's heating and cooling based on these measured temperatures. So if they're significantly too high or too low, again, you're going to condition more energy than you should. But a lot of these sensors also act as safeties, like a low temperature cutoff to keep from freezing a cooling coil. And if that sensor is not reporting correctly, then you could potentially damage your equipment. Now, the challenges of a fault like this, sometimes the temperature has just legitimately not changed. There is nothing wrong with the operation of the unit. It's just how it's operating right now. And you may get a fault even though everything's just fine. Sensor accuracy, type, and location also play an important role in this. If you have an inappropriate ranged sensor or it's in a bad location, it could indicate that there's a problem that maybe doesn't actually exist for the operation of the unit. And then finally, one of the challenges we have is with our legacy systems, sometimes they don't report a change of half a degree. It may be a degree or 2 degrees. And then again, you'll have a fault trigger for that particular sensor that's not necessarily really a problem. Just because it hasn't changed doesn't mean that it's reporting inaccurately. Next slide. So I wanted to give you a little taste of some of the more complex faults that we've put into place. One of the most common sequences that are in place on an air handler is commonly referred to as either economizer mode or free cooling. And the idea is that if I want 55-degree air to come out of my vents to cool a space, then I want to use the least amount of energy possible to hit that 55 degrees. So if my outside air temperature is also 55 degrees, I don't want to bring any air back from the space, and I don't want to heat or cool that air at all because I'm essentially just bringing it in without having to do any comfort conditioning on it. And so we save some energy associated with that. The downside of this is we rely on a lot of sensors in order to detect these conditions. So are we in that happy medium where we want to bring this in? Or conversely, when it's much, much warmer or much, much cooler out, we want to bring in a minimum amount of outside air so that we're not having to overcool or overheat the amount of air by bringing in outside air instead of the air that's coming back from the space. As with the majority of faults, the biggest Achilles heel of this fault is the fact that it might rely on a dozen or more sensors to determine these conditions. And so again, it's really critical that we make sure that all of these sensors are located where we think they are and that they're accurate. Next slide. So for MSU, and I'm stressing MSU because the benefits of any particular system are going to be highly dependent on the organization, what their funding structure is, and what their goals are. But for MSU, because we wanted to primarily self-perform, the pros of a rules-based fault structure for us are it was easier to deploy. You get faster results from it because you don't have to train a model before you start seeing issues. You put a rule in place, and either the air handler is breaking the rule or it's not breaking the rule. They're easier to interpret because they're laid out in a logical way. And again, it's black and white. Either it is breaking the rule or it is not breaking the rule. And because it's a relatively simple language to implement, they're easy to modify. So if we have a unit where our accuracy of our temperature sensor is 2 degrees, we take that half-degree fault and change it to 2.5 degrees so that we would expect to see a change. And that's really pretty simple with a rules-based fault structure. The downside of a rules-based fault structure is it's heavily dependent on the level of available sensoring. I cannot detect a fault based on information that I can't collect because I don't have a sensor there to collect that data. Also, cascading faults can be more difficult to manage. And a cascading fault example would be if I have a building in the summer that receives cooling from a chiller, and that chiller fails, then we're not going to have the cold water that we need in order to cool the air in all of the air handlers. Well, all of those air handlers are going to trigger a fault saying that the chilled water is not operating the way that it should. And if I have faults at the room level, they're all going to say, hey, we're not able to cool down to our cooling set point, there's a problem. And that could be hundreds of faults that get created when it's really just the chiller that's the problem. Now you can put data checks in place to say, oh, well, you know, if the chiller is not running and the air temperature is above or below a certain point, that we don't want this fault to trigger. But the more checks that you put in place, the more likely you are to mask a real problem if you have a communication issue or if something's commanded on that's not actually running. It's a slippery slope when you start to try and manage those cascading faults. And then false positives really require field validation in the majority of instances. Slide. Did you skip a slide? Can we go back like 2 slides? There should be one with a blue screen with an air handler.
Maybe they're out of order?
I must have got them out of order. I apologize. So, an example of one of these faults that requires field conditions is this leaking heating valve fault. And actually, I apologize. That was not out of order. I got ahead of myself. Can you go back to the FDD implementation prioritizing faults slide? One more back, yeah. I apologize. So once we've detected a fault, we really need to categorize it into one of 3 types of faults. We use primarily monetization. So what is the cost of this fault happening? Is it something that's costing a lot of money, or is it something that really could be pointing out a significant chance of an imminent failure? But there are faults that will be detected that aren't necessarily going to save you money. Maybe it's a fault where we're below the heating set point, and what needs to happen is we need to open the heating more. Well, that's going to cost us money, but it is an operational fault. So we also need to look at, you know, how is this fault going to impact other systems? Or in the case of not providing ventilation, could it possibly be a safety hazard? And then we also classify our faults based on comfort, which is purely if this fault is not addressed, are we going to have more calls to technicians because it's too hot in the building or it's too cold in the building? Slide. So I wanted to add a little bit extra about fault monetization here. There is the most common type of monetization is either they take a snapshot of, and I'm sorry, they, as in the company or the people providing the monetization, they'll take a snapshot of how typical units run, and they'll estimate the energy associated with conditioning that air and moving that air, or they may take information related to an actual unit, but again, they kind of estimate that energy associated with it. They pick a period of time that they believe that the fault would not be addressed for, and then they extrapolate that to a dollar amount, saying, okay, well, if this fault happens anytime during the year, then we're going to see this many dollars of impact. And it's something that MSU fundamentally disagrees with, because if we have a chiller fault in the middle of winter when it's 5 degrees out, that chiller fault is not going to save us any money because that chiller is not in operation. So what we did for our monetization was actually we run calculations using the fan affinity laws and the pump affinity laws, as well as some BTU calculations, so that when a fault triggers, we are still estimating how long we think a fault would not be addressed, but we're using data that is current to how the unit is operating today. And so at the very least, if it's in the middle of winter, we're not going to say we're going to save thousands of dollars from a chiller operational fault. Or if it's in the middle of summer, we're not going to have an operational fault for the heating valve isn't heating properly because we don't need heating for that season. Slide. We also have some challenges here at MSU in addressing our faults. Our primary one is an infrastructure challenge. So with a large number of faults, you need to have staff that are able to address the faults. That's everybody from the people who are receiving the faults from the system via notification dashboards to the control staff to look into the programming of the system and the set points to determine whether or not this is an issue with a sequence of operation and how the air handler should run, to tradespeople who, if we determine that it's not something with a software issue, we need somebody to go out there and turn the wrenches and screwdrivers in order to figure out what the problem is and fix it. We also have not established a good workflow and how to handle faults. So in an ideal world, a fault would trigger and it would get directed to whoever the appropriate entity's workbench is. They would automatically pick up that work order and then they would run out into the building and then they would address the fault. They would record what the problem was and then they would come back and tell us, closing a loop that gives us root cause analysis. It's not something that has been well established yet. We're still working our way through what that should look like. The other challenge that we have with addressing faults is interpreting them. So the issue is we can have a rule that detects a particular thing. We can assume that it is a particular problem, and that's just not always true. Slide. So an example of that is the slide that I jumped to earlier. But the example of that would be this leaking heating coil valve. So the assumption that we make here is we have a fault that triggers. And as you look at this, this is a typical H pattern air handler. You don't really need to understand it significantly, but you should see that the air coming into the heating coil is 56 degrees. We see that the heating valve is commanded shut, so it shouldn't be heating at all right now. You can also see that the heating coil, the discharge of the heating coil is 65 degrees, and we're trying to meet a 60-degree set point to the space, but we're actually getting 72 degrees. So at face value, it's easy to look at this graphic and say, oh gosh, that heating valve's leaking by, we need to replace it. In reality, we have replaced the heating valve on this unit twice, and because I knew that that had happened, what we did instead was we went out in the field, we took IR images, and we took readings around the air handler, and what we discovered was in this particular mechanical room, there's a very large steam pipe that runs over top of the air handling unit, and some of the insulation was no longer in place. It was actually creating enough heat to the top of the metal in the air handler that we were seeing a significant increase in temperature, but the heating coil valve was just fine. Slide. So to wrap up where MSU, what direction we picked and where we're currently heading with it is, we went with a rules-based fault detection system because it was cost-effective since we're performing the vast majority of it in-house. It meets our expectations for development because we are the developer. And so making changes or building new things is a relatively simple process for us because it's us. Customizing faults internally was also a strong motivator for how we originally decided to go because we have a lot of very old systems or quirky systems that kind of require massaging of faults in order to get good results. And we wanted better control of the monetization of the faults because when we project an energy savings, we are expected to produce that energy savings. So a gross estimate just wasn't something that was going to work out for us very well. It's also been a challenge because we have a bit of a lack of staffing to respond to large volumes of faults. Most of our really experienced staff are tradespeople or controllers that already have a full-time job, and now we're asking them to pick up this little bit extra in order to help grow the pilot. Training can be complicated, again, because they're busy and this is not their primary duty. And then where we want to go for our next logical step is predictive analysis. And we simply don't have in-house staff to move in that direction, which means that we're either going to have to find in-house staff to perform that, or we're going to have to look to third-party firms in order to build the predictive analysis models for us. Slide. So program suitability, I'm not sure if this is an issue that is going to come up for you, but I wanted to share that, you know, across the Big Ten, there's dozens of universities that have different fault detection systems, and a lot of them are quite varied in their application due to the factors that those particular entities wanted. You know, some of it is based on staffing and funding structure. So how much are you willing to spend to either retrain or hire new people? How much are you willing to spend on a faster implementation or a more expensive solution? You know, one of the others is the level of engagement. So if you have a really engaged upper level of stakeholders, you know, your VPFOs and such, you know, how fast do they want to do it? How far do they want to go? And who do they want to do the work? There's also the level of current and future instrumentation. So if you don't have very many sensors on your equipment, then you're not going to get very much bang for buck from fault detection. So are you going to spend the money to have more information available, or are you going to aim for a cheaper solution that you know, is going to give you at least some results? And then finally, you know, it's the desired level of direct intervention. So does the organization want a hand in development, or do they really just want to get the reports that allow them to go out and address the problems faster and see bigger bang for their bucks? Slide. So that's pretty much all for me. I did, in a little conversation prior to this, I was asked to talk about dashboards just a little bit. One of the things that we found at MSU is that, you know, it can be really difficult building dashboards for different stakeholders. You know, one of the first things that I hear when I engage a different group for, you know, what they'd like displayed is, well, we don't really know what we want. We're not really sure what it should look like, but, you know, we're pretty sure we'll know what we like when we see what we like, which can be difficult to develop for. So as you are working through your project, I would just put some thought towards what visualizations are actually going to be valuable to the stakeholders versus what visualizations may be really cool, and you know, they might have a lot of you know, really interesting animations and things to them, but nobody is really going to use them for anything. And while that might help with the sales pitch, it really hurts over the long run because people will just write the whole solution off as gimmicky. And it's just some food for thought as you're going forward. So I thank you for your time. You can feel free to contact me at the email, and that's my desk phone number there. I'm happy to talk about this further if anybody desires. I think that's it for me.
Great. Well, thanks, Jared, so much. And yeah, I appreciate you sharing those thoughts on dashboarding. I was kind of curious too, and I know it was part of our conversation that you and I were having, but you talked about how it's difficult to engage some of the management or decision makers at MSU. Could you share some of the solutions that you presented to help them think about the decision to go forward with the AFDD tools that you are using? What kind of visualization did you use in your case?
Well, it's actually a little awkward because we didn't use any visualization to get them to greenlight the pilot. We actually used good old Excel and graphs in Excel.
Okay.
partially because at the time we were not particularly adept at building graphics, but partially because a lot of the stakeholders that we were engaging are just used to seeing things a certain way, and Excel was the easy way to provide it to them in the way that they expected to see it. And we get better response from them when they see what they expect.
Yep. So were there particular pieces of information within those Excel files that were kind of the clincher on helping them make the decision, something like, return on investment or, lost money or something like that?
Yeah, our primary driver when we made the case for the business case for the fault detection was primarily utility savings. So we projected a really conservative 2% reduction in the buildings that we piloted in, just based off from faults. We did add in, the anticipation of a reduction in labor cost. So less trouble calls, less time spent on site, because we've, done some of the legwork via fault detection for some of the issues that mechanics might otherwise have to search around for information on. And then there's also, the forward-facing view on this when we're finished and able to publish it to campus. The optics are nice to be able to say, look, we're doing all these cool things. Here's cool dashboards. Here's benchmarks of utilities in your building. Here's benchmarks of equipment operation versus other types of equipment in other buildings or other campuses. But it's extremely difficult to try and assign a specific savings number to either of those, which is why we think monetization was the most important piece of the puzzle to nail, because that makes sense to everybody.
That's great. Well, so if you have questions for Jared or for me, feel free to type those into your chat button or chat window. While you're thinking about those, I'm going to share some more information about our challenge here. The recorded webinars are up. I'm actually going to go over there to show it to you right now, if I can make this window work. Hopefully you're still seeing my screen. So this is the current round 2 challenge. Get rid of that window there. So fault detection. Just a reminder that what we're looking for here is a review of the data sets that are down below, right here, to download those and look at them and think about what kind of faults, try and figure out what kind of faults they are and when they occur, a method for identifying or indicating how to identify the fault per different level of available data, the energy savings potential by fixing the fault, and a method to help the owners visualize the fault through data or another method. So what would be a good decision-making piece of information for them? And then this looks like, yes, no, this is right. So view the webinar. This is a recording of the first webinar that occurred last week and another webinar that occurred last week. Both of these are great pieces of background information. Today's webinar, or at least a portion of it, Jared's, will be right here, so you can check back on that. So let's go back to the slides. And I want to do a final plug for our round 3 challenge. Some of you may have heard about this. This is going to be on wall retrofit solutions. We expect this to be up and launched this week, so do check back. We will make an announcement about that. What we'll be looking for is the use of a base case house to design a wall retrofit product that will meet local code, address material needs, efficiency levels, air tightness, etc. Also to demonstrate performance for moisture and air tightness requirements, and of course, looking for improved energy performance. Checking back to see if we have any questions in our chat field here. I don't think we have any questions that have come in. If you do have questions that come in later, you can reach back to us through the questions button at the bottom of jump.ideascale.com. And with that, I want to thank Jared for your time today. Great presentation, a really fantastic program at MSU. Congratulations on that. And I hope everybody has an awesome afternoon. Thank you.